Okay, we're going to take a look at section 7.1, day 2, and this is going to continue our lesson on right triangle trigonometry. We need to begin today with a little lesson on bearing or directional measurements. If you look closely at this picture, you're going to see that point 1, P1, is on a arrow or a vector heading off on a direction that is listed as north 30 degrees east. So you can see where directly north was, and then that vector, that line, is going 30 degrees towards the east. So that's how they label that vector, that direction, north 30 degrees east. Well, keep in mind, if that was 30 degrees, the angle on the other side of this would be 60 degrees. So we could also label that as going east 60 degrees north. Same direction, same bearing measurement. Let's take a look at point 2, P2 over here, and let's get a bearing measurement for that, bearing direction. So we could start by saying going north, but it's not going directly north, it's going 70 degrees towards the west. So that bearing measurement would be north 70 degrees west. Or, because 70 degrees is there, we could put in and say, okay, well, if that's 70 degrees, then right next to it, its complementary angle is 20 degrees. So the same bearing measurement, same direction would be going west, but then heading 20 degrees to the north. So we'd say west 20 degrees north, same bearing direction. So let's start out here with a problem involving bearings, bearing direction. A Boeing 777 aircraft takes off from O'Hare Airport, that's in Chicago, on runway 2 left, which is a bearing of north 20 degrees east. Okay, so let's draw that direction. So I'm going to just kind of do a little dotted line as if I was going straight north, but no, we're heading 20 degrees east of there. So the direction is going 20 degrees off towards the east. So there's a 20 degrees in here off of that going straight north. After flying for 1 mile, the pilot of the aircraft requests permission to turn 90 degrees and head towards the northwest. So they've traveled 1 mile that direction, then they're going to turn, and then they're going to head off to the north west. Okay, after the plane goes 2 miles in this direction, what bearing should the control tower use to locate the aircraft? So now they're traveling that way 2 miles. Let's see if I can maybe make this whole thing move down a moment here. Oh, great. That wasn't great. There we go. Okay. So O'Hare Airport's down here. And when they get all done, the airplane is up there. They want to know what's that bearing direction. Well, we need to figure out what this whole angle is in here. I'll put theta right in there. We're going to figure out that entire angle. Here's the right angle. With respect to that angle theta, we have the adjacent side, we have the opposite side. So we're going to do is use tangent. We'll say tangent of theta is equal to opposite, which is 2, over adjacent, which is 1. Let's figure out the size of that angle. Now we're looking for the angle, so you're going to use your inverse tangent. So second tangent, so I'm doing inverse tangent of 2 over 1, or just 2. And I'm going to get 63.4 degrees. So that means this angle right here is 63.4 degrees. It's a whole angle. Now, if we want the actual bearing measurement, what direction? They're not going straight north, they're going how many degrees off towards the west? We'll take the 63.4, subtract off the 20 degrees, and we'll be left with 43.4 degrees. And that's what's the angle that's left right in there. right in that little, how much they're going towards the west. Okay, so what's the bearing measurement? Well, they would be going north, but then they're going to be going 43.4 degrees west. They're verging off to the west a little bit. That would be the bearing measurement for that. Okay. The next problem here. A state trooper is hidden 30 feet from a highway. 1 second after a truck passes, the angle between the highway and the line of observation from the patrol car to the truck is measured. So I'm going to move this little picture up here for a second. I'm going to draw a little bit better triangle picture, but you can kind of see what it's doing there. So first of all, we have a right angle right there. And so the angle that they're measuring is right in this corner here. There's 33 or 30 feet, that's a feet there, from where the cop car is to the road. So there's 30 feet there. The time to travel along in this spot here is 1 second. But that's what we're going to first of all find, is we're going to find that x value. Okay, if the angle measures 15 degrees, how fast is the truck traveling? Keep in mind, we want to find out, in this case, we'll find out feet per second. So if we can find out what that distance right there is for x, that will give us the feet that they traveled in that 1 second. Well, we know right now that this theta right here is 15 degrees. So let's take a look here. With respect to that angle theta, again, the 30 is opposite, and the x, which is what we're looking for, is adjacent. So opposite and adjacent, we're going to need to find a tangent. Okay, so I'll put that over here. We're going to figure out the tangent of 15 degrees is equal to opposite, which is 30, over adjacent, which is x. Okay, the x is in the denominator, so to solve this, I'm going to have to switch those around. So x will equal 30 divided by the tangent of 15 degrees. So we'll plug that in. 30 divided by the tangent of 15 degrees. And we're going to get 111, that's 112 feet. 112 feet. So x is equal to 112 feet. So that's the distance that they traveled in 1 minute. So we already have our speed right now, traveling 112 feet per second. That doesn't really tell us how fast they're going. We're going to have to make a little conversion. Now let's remember a few of these that we know. We know that 1 mile is equal to 5,280 feet. Okay, so I'm going to use that first conversion there. I want my feet to be gone, so I'll put the 5,280 feet on the bottom and the 1 mile on top. Okay, the other thing we know is that 1 hour is equal to 60 minutes, and each minute is 60 seconds, so 60 times 60, 3,600 seconds. Okay, so I want my seconds to cancel out, so I'll put the 3,600 seconds on top over my 1 hour. I'm going to take out my other stuff here, make a little room. Okay, so what is this telling me I'm going to do? I'm going to multiply the 112 times the 3,600. So 112 times the 3,600. And then on the bottom, if you recall, there was the 5,280. So divide it by 5,280. And we're going to get 76.4. So we're going to get 76.4. But we're left with, the feet are gone, the seconds are gone, and we're left with miles per hour. So this conversion told us to multiply by the 3,600 and divide by 5,280 feet. The guy was speeding. He's going 76 miles per hour. Find the distance from A to B. it must be a pond there or something, and they can't measure directly across, so they're putting some other measurements in there. I'm assuming that this line coming straight down is a right angle, so we actually have two little right triangles. Next to the 110 is 70 degrees, and next to the 140, of course, makes a straight line, would be 40 degrees. Well, if I can find the distance from point A to that altitude, I'll call it X. If I can find that distance, and then if I can find B to that same point, I'll call that Y. We can just add them up. We'll look at the right triangle on the left. With respect to the 70-degree angle, X is adjacent. The 3 is the hypotenuse. Adjacent and hypotenuse, that's going to be cosine. So cosine of 70 degrees will be adjacent over hypotenuse. If we look at the other right triangle, the one on the right, with respect to the 40-degree angle, again we have adjacent, and then the 5 is the hypotenuse. So we'll go with the cosine of 40 degrees is equal to adjacent, which is y, over hypotenuse, which is 5. Let's plug those in. Cosine of 70. So the cosine of 70, I know my angle. I will take it times. In this case, I was taking it times the 3. And we're going to get 1.02. So x will equal 1.02. Now let's find the y value. So cosine of 40, we're going to take it times 5. And we're going to get 3.83. So that's what y will equal. And if I just add the two together, we're going to get a total distance from A to B to be 4.85, and we were dealing with miles. And you should look to see, does it make sense in the picture? Hopefully it's somewhat drawn to scale, but you're kind of coming up with an answer that makes some sense. Okay, you can see at the top of this next page, there's the assignment. One of the problems you're supposed to do is number 60. I actually provide the answer there, but let's set it up, and then you be sure to show the work to solve it. Okay, a ship leaves the port of Miami with a bearing of south 80 degrees east. So here we have Miami. So instead of going directly south, okay, it says south 80 degrees east. So there's an angle going off of there of 80 degrees. So in here, that angle opening up, that's 80 degrees. So instead of going straight south, they're going 80 degrees towards the east. Okay, then it says they're traveling at a speed of 15 knots. When that means they're going 15 nautical miles per hour. That's what 15 knots means. 15 nautical miles per hour. After 1 hour, the ship turns. So they did go that whole 15 knots because they traveled 1 hour. Then they're going to turn. The ship turns 90 degrees towards the south. So they're turning 90 degrees, they're going towards the south. So here's a right angle in here. That my angle doesn't look very right-like, but it should be. Towards the south. After 2 hours, maintaining the same speed, what is the bearing to the ship from the port? So if they've traveled for 2 hours, that means they're going to go 2 times 15. They will have gone 30 nautical miles. Okay, I'm going to then connect to make the triangle, okay? And we'll call that, there's the boat down there, or the ship. So we'll put S for ship. Okay, they want the bearing measurement, the bearing direction from Miami to the ship. What direction is this line that I'm now highlighting in red? What bearing measurement is that? All right, show your work, draw pictures, show your work, show the equations, and so on.